So the main idea, again, assuming you went over this, they're just using the constant proportionality to create the differential. So what you're going to do in the homework is they're going to give you some information. They're going to say, okay, well, the culture initially has P naught at T1, so this is the initial condition that you're going to use to solve the IVP. And then they give us another point. They say after such and such, this happens. So at time 0, we have P naught. At 1, we have 3/2 P naught. So those are actually 2 points, which will help you solve for K. Anyway, but what really matters is right here. There's the term. If the rate of growth, here it is. So if the rate of growth is proportional to the number of bacteria at present time t, determine the time necessary. Okay, so that first part. If the rate of growth is proportional to, so what they're saying is the differential equation is equal to some function k times k. So in this case, it would be the rate of growth, meaning dp dt, right? That's what rate means. Derivative of p, the growth function of bacteria, would be equal to p times some constant. So all they did was move this over here. So they subtracted. So they create a differential equation by reading that sentence. dp dt, the growth is proportional to, this tells you equal to k p. Does that make sense? Where this came from? See, do you see how this sentence gives you this? So same thing over here, right? Find the half-life of this isotope if the rate, keyword, is proportional to the amount remaining. So all right, well, decay, dA dt, the rate is equal to the amount A times some proportional, times some constant of proportionality. That's what this is telling you. So like back in, I think college algebra, we would say, when you would read the proportional constant or the word proportional, that would be equal to something times k. So that's how they create this. So in the homework, you're gonna have to make this yourself. And once you make this, you use the initial condition that's given to solve the DE. Okay, so that's all you're gonna be doing over and over again. So given some information, create the differential. Anyway, I'm assuming you've hopefully started that already. I'm gonna move on to 4.1 though. So look over the videos by what's his name? I want to call him Zod, but that's wrong. Shoot. Oz, that was it. Okay. Anyway, so 4.1 is very theory heavy. It's more about definitions and ideas. Not the solving part is pretty easy, really. So let me just write down some theorems. So we have them. So this one is existence of a unique solution. That an of x all the way to an minus 1 ax till a1x comma a0x and g of x be continuous. On an interval I, and let an of x not equal 0 for all x in I. I should say, yeah, I. So if x is equal to x naught, if this point, x equals x naught, is any point in this interval, then a solution y of x of the, I'm going to use an abbreviation IVP. We've been talking about initial value problems for a while now. IVP exists on I and is unique. So to put this in plain English, this theorem is telling us is that if you have a specific point initial condition and you solve for IVP, you solve the IVP, it will be unique. Which makes sense, right? Remember we were talking about those fields and how there's families of solutions, right? So when you have a specific condition, you end up finding one specific solution instead of a general solution. So eventually we'll be talking about particular solutions, but it makes sense that it's going to be unique because we're using an IVP. So in my head, I just think about, okay, well, obviously it's unique because it's a specific one, right? Just to put it in plain English. Okay, I'll give you a few more theorems here. I'm assuming everyone remembers what linear is defined as. So let me give you some definitions. There are. This one will be pretty important when we start solving higher order differential equations. So superposition principle for homogeneous or homogeneous, whatever, depending where you live. Okay, so let y1, y2, y3, all the way to yk be solutions of a homogeneous nth order differential equation. Okay. We're going to call it star. I'll write star down in a second. The D there, the general D that we're talking about, it's called star. On an interval then the linear combination y equal to C1y1 plus C2y2 plus all the way to CKYK, where CI are indexes from 1 2 all the way till k. So all these are arbitrary constants. So this guy right here is also a solution on I. Okay. So what this is saying, that if you have a bunch of solutions, let's put this in plain English as well. Oh, let me give you a star first. In the book, they give you a general nth order. So this is the one they're talking about. An of x times dy, dn dy, sorry, the nth order derivative, right? Plus an minus 1 of x times dn minus 1 dx minus 1 all the way to the first derivative until you get to the constant. So this is said to be homogeneous. So homogeneous because it's equal to 0. So if you had the exact same thing, double star, let's just put quotes so we don't have to write it again. If it's the exact same garbage equal to some function g of x, this would be non-homogeneous. Okay. Now, anyway, back to the theorem. I just wanted to make sure that we had defined homogeneous. I don't remember if we have or not, but here it is. So if y1, y2, y3, all the way to yk, if each of these are all solutions to a homogeneous equation, differential equation, then you can find a linear combination of them, right, back from linear algebra, where you have each y1, y2, all the way to yk times some arbitrary constant all together combined. This will also be a solution on I. So together, separate, etc., all solutions. Okay. So that's one theorem, two theorems. A side note that branches off of 4.12. Separate this right here. Separate that. You guys cool on this theory page so far? So I can turn the page. Okay. Right. Corollaries from your book. A constant multiple y equal to C1 Y1 of a solution Y1 of a homogeneous linear differential equation is also a solution. So basically what we just said earlier, if y1's an answer or a solution to your DE, multiplying times some constant is also a solution. Plain English. Also a homogeneous linear differential equation always possesses the trivial solution. And by trivial, I'm sure you remember, is y equal to 0 as a function. All right. Does everyone remember what? Well, let's see before we do that. So in the homework, we're going to have you verify some solutions, very similar to what we did right at the beginning. So I don't think we need to go over that again. Now, I think example 4 might be more interesting. Try to get an idea of what the superposition means and why it's important. So basically in example 4, they give you 2 solutions to the DE, which means that you can create a linear combination yourself and technically solve for the C constants, assuming they give you initial conditions. So the functions y1 equals x squared and y2 equals x squared ln x are both solutions of the homogeneous linear differential equation, which is going to be this guy. X cubed times x cubed times y triple prime minus 2x y prime plus 4y equals to 0. So the main idea they want you to understand from this question is that you can create a linear combination. So since y1 equal to x squared and y2 equal to x squared ln x are both solutions, then by the superposition principle, right, by, we called it 4.12, then by 4.1.2, this is also a solution, c1 x squared plus c2 x squared ln x. Does that make sense what the superposition is talking about? Okay, let's see here. It's not really much to solve here. Again, it's very theoretical. I'm hoping you read the definitions a little bit. Next definition. 4.1.1. Linear dependence / independence. So a set of functions f1, f2, all the way till fn is said to be dependent on I, some interval I, if there exists constants C1, C2, Cn, not all 0, such that C1, F1, I'm not putting the f of x, it's implied. These are all functions. C2, F2 plus Cn, Fn is equal to 0. For all x in the interval I. But if that's not true, if the set of functions is not linearly dependent on the interval, it is said to be linearly independent. So in the moves, we're going to show how we prove that two functions or two solutions are independent. Okay. So that is to say, the set of functions C1F1 plus C2F2 CNFN is equal to 0 for every x in I, such that C1 equals C2 equals C3 equals ... Cn equals 0. Right. See if I can find a good picture here. 1 second. So let me show you how you show uh, if something is independent. So basically you have to do a Wronskian. So if the Wronskian is not equal to 0, then the functions in question are independent. So you can test them all at the same time, but the more functions you have, the bigger the matrix you get, the more complex the determinant. Here's the Wronskian. You guys cool on that page? Let me know if you need me to turn back. So suppose f1, f2, all the way to fn are functions with derivatives up to n minus 1. The determinant of the notation you use for the Wronskian is W of f1, f2, all the way to fn. So you do a giant determinant, f1, f1 prime, all the way till f to the f1 to the n minus 1 derivative. That looks ugly. Fix it. f2, f2 prime, so if you had if you had, let's say you had two functions and you wanted to test, are these linear? You would put the first one here, second one there. I should say two solutions, but same thing. Take one derivative up until n minus 1, so you would take just one for two derivatives for three functions, and so forth. Then you take a determinant, right? And if it's not 0, then they are linear independent. So if the Wronskian of all of these guys does not equal 0, then f1, f2, fn are all independent of each other, or linearly independent. Okay. So then you can figure out, okay, when they ask you a question like, okay, are these solutions independent? Alrighty. So let's see if find an example where we can test it. Yeah, example 7. The functions y1 equal to e to the 3x and y2 equal to e to the negative 3x are both solutions of the homogeneous linear equation determine if they are linearly independent. Okay. So the Wronskian of y1, y2 is equal to okay, here's the second function. So the first derivative would simply be, so if I have two of them, then I have to take n minus 1 derivatives, where n is 2, so that'll just be one derivative, right? So 3e 3x negative 3e negative 3x. So the determinant doesn't have to be that big. You guys remember how to take determinants? Or just a 2x2, can't be too crazy. The ones that suck are those 3x3s. Or once you pass 3, it's even worse, but it might give you anything larger than the 3 on an exam. Honestly, 2 should be the minimum, but for the maximum. But we'll see. So you do this guy times this guy, e to the 3x times negative 3 e negative 3x minus e to the negative 3x times 3 e to the 3x. So multiply this out. See if the determinant is not 0. Let's make sure I wrote that correctly. Yes, if they're not 0, then they are independent. So let's see if they are not 0. So e to 3x and e negative 3x, that cancels, giving me a negative 3. Minus this guy gives me another 3. That's the ugliest 3 I've ever seen. That would be negative 6. Which is not equal to 0. Therefore, y1 and y2 are linearly independent. So for sure in your exam, you're going to have a question like that. Exam 2, I guess, where I give you 2 solutions and I ask you determine if they are independent. That's all you have to do is create a Wronskian, take a determinant, and check if it's 0 or not. If it's not 0, cool, not independent. If it is 0, then you say dependent. Any questions on this idea? The last two important theorems here is going to be the general solutions for homogeneous and non-homogeneous. And then after that, we should have enough theory to start solving problems. But I highly recommend you read through them as well, just in case. There's more details in the book. I'm going to mainly focus on the non-homogeneous because it's basically the same. They're just an extra piece. So let me show you in a moment. Excuse me. One second. Okay. So general solution to a non-homogeneous equation. So and again, remember what we said what a non-homogeneous means, right? We said that is a nth order differential equation that looks like this, but it's not equal to 0. It's equal to some function. Okay. So that's the only difference. It's this guy right there equal to some function g. So assuming that's what we're talking about. So the solution to that guy in general will be defined by this. So let yp be any particular solution of the non-homogeneous linear nth order differential equation. And that's the one I just pointed out earlier. So yp be any particular solution of the homogeneous equation on an interval I, and let y1, y2, y3 till yn be a fundamental set of solutions of the associated, so we just refer to it as double star. We're writing way too much and try to shorten this up. Double star. Where was I? Shoot, lost my train of thought there. Okay. Solutions of this guy on I, then the general solution of the dE on I is the following. So y is equal to c1y1 plus c2y2 dot 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 cnyn plus yp, where ci, remember, these are all just arbitrary constants, where ci, comma, ci, comma, I is equal to 1, 2, 3, till n are arbitrary constants. Okay. So the only difference between the homogeneous and non-homogeneous is you have to add a particular solution. Okay. So if it is in fact equal to 0 and not some g function, then all you need is this piece. But if it's not equal to 0, it's equal to some g function, then you need to solve for, you need this piece plus this piece. Okay. So we can also call this right here the homogeneous solution, and this guy is the particular solution. So together they create the general solution. Okay. Is there any questions about that? There's a lot of theory in there, so please read through it and think about it. We can talk about it all day long. Okay, now we have how much time left? 1 sec. Let me show you what the homework looks like. It's not too bad, I promise. And I want to look through it too, just in case there's a crazy question in there that shouldn't be. So number 1, given the family of the functions, given family, of functions, so this guy right here is a solution. Find a member of the solution of the IVP. So basically they're asking you to find a specific solution. Remember how we said there's a unique solution? That's what they want you to find. So they give you the solution. You use these initial conditions to solve for C1 and C2. Okay, 1 moment. Okay, so the next part, same deal. They give you a solution. This is a family of solutions, meaning this represents an infinite number of solutions. The initial conditions here will help you find a specific one. Okay, so they just want you to find that specific thing. So super easy compared. It's basically the same thing we did at the beginning of the semester where we solved for C1 and C2. Okay, it's just now it means more because we're studying more of the theory. So just go through this and practice. Okay, so same thing here. So nothing insane. Okay. I don't think we're going to do anything with the boundaries. I'm going to get rid of this guy. Here, though, here they give you two functions. You need to show that they're independent. So you're going to do the Ronskin. Here, there's three of them. So you'll have a 3 by 3 determinant. 3 by 3 determinant. Okay. All right. Same deal here. To show that they're independent or dependent. So taking those derivatives, taking the determinant will prove that for you. Okay. Okay. Anyway, that's pretty much it for this section. I mean, the questions are not that hard. I think what's hard is you reading through the section and understanding what they're talking about. So please look it over. Even if you can do the homework, no problem. I need you to look over the section, okay? Those ideas will be in the background for all of chapter 4. So next time, we're just gonna move on and start hitting chapter 4 pretty hard, solving higher order differential equations. So first, we've only solved first order, so then now we're going to start solving second, third, etc. Okay. You guys have any questions on these definitions or these ideas? Right, I guess. Well, I'll see you Monday. I extended the exam. That doesn't mean wait till the last minute. It should be done today. But I pushed it to Sunday. That way you need to make sure that you can access it. It works, because if you start trying doing it Saturday or Sunday and it doesn't work on your end, I'm probably not going to respond because it's the weekend. So I recommend trying to do it Friday. If there's any issues, then we can figure it out then. But please get it done soon. So it's still open until Sunday night. I'll see you guys Monday.